And so off we go. Doug, whenever you're ready, go ahead and start sharing your screen.
You got to enable me to share.
Oh, yeah, I always forget about that. Make co-host.
Yeah, it's rough being a host.
Nah, it's just a button.
Well, the other night I was hosting a meeting and I accidentally ended the meeting on everybody when I was just trying to leave it.
Doug and Steven, yeah, you are both co-host now, Doug and Steven, so you should be able to share. I'm going to mute a couple of people who are unmuted just so that we don't have any interruptions. So please mute yourself when you are ready to ask a question. And I can see your screen share, Doug, so you should be good to go.
Okay. So I went through and picked out the constellation Lynx because even though it's a northern hemisphere constellation, no one had done it before. So I thought I'd pick it. But of course I have to start off with some comedy. So I love this one. Edwin Hubble's car, on his mirror, it says, "Objects in the mirror are bluer than they appear." Only an astronomer could love that, because all the objects in the mirror are receding, so they're redshifted, so therefore they're actually bluer than they appear. Love that one. Astronomer humor. Okay, so constellation Lynx, it's located in the northern hemisphere. It's a very large constellation covering 30 degrees in declination and 3 hours in right ascension. It's actually the 28th largest constellation in area out of the 88 constellation. It lies between Ursa Major and Auriga, basically. If you look at the chart, you can see where it is. It's in the 30, 40, 50 degree declination, Ursa Major on one side, Auriga on the other, Gemini, Cancer, and so forth to the south, Camelopardalis to the north. Now, Lynx is an interesting constellation historically. It doesn't have any Greek heritage, even though it was clearly visible to the Greeks. It's leftover stars, basically, is what it is. It's just a collection of stars between those major constellations that I mentioned, that when they drew constellation boundaries and they formalized the constellations like Ursa Major and Auriga and the other major constellations, there was a large group of stars that didn't fit in, and they put them in their own constellation and called it Lynx. And the reason it was named Lynx is because one of the astronomers who was working on it called it Lynx because it's very faint, and he said you need to have lynx eyes, essentially really good eyes, in order to see the stars. It was first published in a catalog in 1712, and then published in atlases after that. And some of the stars were stolen from Ursa Major, some of them were stolen from Auriga. It's just leftover stars.
So the name Johann Hevelius rings a bell from, I think, a couple of other constellations we've had in the past.
Yes, he helped develop some of the constellation boundaries during his time. He formalized some of them, along with Flamsteed and some of the other astronomers of that period. They sort of eventually formalized on constellation boundaries and names, taking the stuff from the Greeks and coming up with things. So, but you know, one of the things I find interesting, just to give you an idea, is the charts are so weird. Like these two charts are from different atlases, and they showed links different in each way using different stars. And it's like, you know, if you go back to this chart, good luck getting a cat out of that, you know, really. It's just a group of, it's just stars. There's no shape or anything to it. It's just leftover stars. Okay. So it's an easy constellation to miss because there are no bright stars. There are no stars brighter than magnitude 3 in the constellation. When Flamsteed made up the stars, he counted there were 44 stars in the constellation, but today we now know there are actually 97 stars brighter than magnitude 6.5. And because of the large area that it covers and the fact that it's not in the Milky Way, there's actually a lot of interesting objects, galaxies mostly. And as it turns out, Lynx is also very rich in double stars. It's a favorite target for people who do double star work. There's several really nice double stars in Lynx. I'll talk about some of the brighter stars, of which there are not many, like I said. So Alpha Lynxus is the only star that has the alpha, beta, gamma designation. It's the only star that has that designation in the entire constellation. It's only magnitude 3.14, so it's not terribly bright. It's an orange giant. It's about 200 light years away from the Earth. It's twice as massive as the sun, but it's exhausted all its hydrogen and it's off the main sequence. It's about 55 times the size of the sun, and it's emitting about 673 times as much energy, luminosity. It is fairly cool. It's only 3,800 degrees Kelvin. And it's circled there on the chart. That's Alpha. That is the brightest star in the constellation. The only star that has a proper name is Alcia Cat, Arabic for thorn, otherwise known as 31 Lynxus. It's located 380 light years from the Earth, and it's also an evolved giant, around twice the size of the sun, mass. And it's about somewhere between 59 and 75 times the size of the sun, and about a little over 700 times luminous. It's a variable star, ranging in brightness by a very small amount, 0.05 magnitudes, with a period of 25 to 30 days. And its baseline magnitude is 4.25, and I circled it. This star used to be part of the constellation Ursa Major until the boundaries were officially established. So it's actually, the star still carries the name 10 Ursa Majoris. It's the third brightest star in the constellation, magnitude 3.97. It's a yellow-white main sequence star with a, I don't know why I got magnitude 4.11 there. Oh, it's a binary. Okay. They're 10.6 astronomical units apart, orbit each other every 21.78 years. And it's approximately 52 light years from Earth. It's actually pretty close to the Earth. Why Lynxus? This is a popular target for variable star observers because it's a semi-regular variable. Ranges in brightness by 2.5 magnitudes up and down, 6.2 to 8.9, with a period of roughly 110 days, but there's a longer period in there too. It's a red supergiant, about 580 times the size of the sun and about twice as massive, and is about 25,000 times as luminous. And that's the one down there in the corner, the little red circle. And one Lynxus is also known as UW Lynxus. It's a variable star. It's visible to the naked eye as a faint reddish star, apparent magnitude 4.95. It's a red giant. Slow, irregular variable. 2 periods, one 35 to 40 days, and a second period 47 to 50 days. It's 156 times the sun's radius and about 2,800 times as luminous as the sun, with a temperature of 3,400 degrees Kelvin. And that's way up there in the top corner. And in 12 Lynxus, this is a double star again, has a combined apparent magnitude of 4.87. It's separated into 3 stars. 2 components have magnitude 5.4 and 6.0 that are 1.8 arc seconds apart. And there's a yellow star of magnitude 7.2, which is 8.6 seconds apart. So this is a really nice triple star to look at with a telescope. You could separate all 3 of them and see them on. They're different colors, which is nice. The period is somewhere between 700 and 900 years, and it's 210 light years from the Earth. As I said before, the Milky Way doesn't run through Lynx, so there are no Messier objects in Lynx. Because of its large size, there are a large number of deep sky objects. However, the majority of them, they're galaxies, and they are beyond the grasp of amateur telescopes. I will talk about the ones that you can see with an amateur telescope. Give me 1 second. I'm having one trouble here. This. Thank you. Okay. Okay, so the first one on the list is NGC 2419. This was discovered by William Herschel on New Year's Eve, 1788. It's about 300,000 light years from our solar system, and is roughly the same distance from the galactic center. It used to be called the Intergalactic Wanderer because there was a time when when astronomers thought that it was not in orbit around the Milky Way. It's a globular cluster, by the way. I'm sorry, I should have said that. As it turns out, it is orbiting around the Milky Way, but it takes it farther away from the galactic center than the Magellanic Clouds. So it's in a pretty extreme orbit. It takes 3 billion years to make one orbit around the galaxy. It's 9th magnitude in a telescope, easy to see. But intrinsically, it's actually one of the brightest and most massive globular clusters in our galaxy, having an absolute magnitude of -9.4 and being 900,000 times more massive than our sun. If you looked at our galaxy from Andromeda, this would be the brightest globular cluster you would see in our galaxy from outside. And there's a nice Hubble picture of it. It's very big, very large, very pretty. And there's the red circle showing where it's located. NGC 2770 is a really nice spiral galaxy. It's near the border of the constellation Cancer. It was discovered by Herschel on December 7th, 1785. This was the first thing looked at with the Large Binocular Telescope. It has an apparent magnitude of 12. It's a barred spiral. It's very similar to that of the Milky Way in terms of its actual physical properties. The mass is estimated to be about 2 times 10 to the 10th solar masses, which is very similar to the Milky Way's mass. The star formation rate is approximately 1.1 solar masses per year, which is reasonable stellar formation, right? There are several companion galaxies around it, but they're not causing any strange perturbations in the overall shape of the galaxy or its motion, so they're not very large. One of the things that makes this galaxy a favorite for amateur astronomers, surprisingly enough, is it seems to have a lot of supernova go off in it. There have been 4 supernova just in the last like 30 years in this galaxy. One in 1999, one in 2007, one in 2008, and one in 2015. So people who like to observe supernovas and do searches for supernovas, keep an eye on this galaxy all the time because it seems to be very busy with supernovas. There's what it looks like. And there's the location. It's pretty close to that alpha star down there in the bottom corner. And those 2 objects are really the only 2 objects that are within easy looking for an amateur telescope. Basically, all the other deep sky objects are like magnitude 15 or dimmer. There are lots of them in there because of the large area covered by the constellation, but they're pretty dim. One of the more interesting objects that you cannot see with an amateur telescope, I thought I'd mention it, is something called the Lynx Arc. As it turns out, this is the hottest known star formation region in the universe as of October 2003. It's roughly 12 billion light years away. And it's 1 million times brighter than the Orion Nebula, but it's all in infrared and X-ray. You can't see it in visible. It was located using gravitational lensing techniques behind another cluster that's about 4.5 billion light years away. Keck Observatory, Hubble, and so on located it. It contains at least 1 million blue stars that are twice as hot as similar blue stars in the Milky Way. They're very old blue stars from the very beginning of the universe, 12 billion years or more. The surface temperature of those stars is estimated to be 80,000 degrees Kelvin, or about twice as hot as the stars that you would normally find in the galaxy, in our galaxy. And only the stars formed directly after the Big Bang would be considered to be hotter. And the universe was only about 2 billion years old when this star formation region occurred. And that is an artist's impression of what it would look like if you could see it. And there's the location on the chart. And that's all I've got.
Cool. Thanks, Doug. Any questions from anyone before we move on?
Yeah, I really like that area of the sky, probably because I was born in Cancer and I was looking at Cancer quite a bit a couple of years ago. And I noticed, when I went above Cancer a little bit, just nosing around, oh, nobody looks over there very much in Lynx. But actually, I was aware of that that
I-
galaxy 2770 because it was just outside of Cancer. But I didn't know about the globular cluster 2419 that's near Gemini there.
Yeah.
I have to take a look at that because and I love double stars. So I got to take a look at that 12 lenses now. Now you've piqued my curiosity because one of the things I learned about that area of the sky is that with light pollution, for instance, most people can't see the beehive anymore. And then and then Lynx is even more obscure,
Yeah.
kind of being stashed
mean,
in there.
If you look at the stars in Lynx, while there are 97 stars above magnitude 6.5, there's only a dozen stars above magnitude 5. So if you're in any kind of light polluted area, you basically can't see the constellation at all.
Yeah.
You're only going to see
yeah.
the third and the fourth magnitude stars.
Yeah.
And so you're not going to see
Right.
much of it at all.
That's the big, where we see big impact of light pollution is these constellations literally disappearing. I mean,
Yeah.
when you, and it's very common not to be able to see the beehive anymore. And Lynx, forget about it. You need a really dark sky to see Lynx.
You know, amateur astronomers aren't going to look at Lynx very often because there are no Messier targets there. There's only those 2 deep sky targets to look at, unless you have a big telescope that can go deeper than magnitude 15. There's not much to look at, except for, like I said, it is rich in double stars. Because there's so many stars, there's 97 stars of magnitude 6.5. Many of them are double stars, and there's some nice double stars, like that one star that you pointed out is a really nice triple star to look at with different color components. Yeah, so that's the only thing to look at in Lynx.
So Doug, this was one of the ones that I was trying in vain to see for my constellation thing.
For that.
And Camelopardalis, and I was looking and trying to get as dark a place as I could, and there is just nothing there in that part of the sky. But I was wondering if it's considered circumpolar.
No, I don't think so. Well, is it? Let's see. What
Part of
it's
it.
going from 30 to 50. It's not circumpolar for us.
Okay.
It would be if you were farther north, obviously, but not for us.
Definitely not. No.
Yeah.
But
You have to.
Camelopardalis is, I think.
Is it? Yes, I guess so. Close. Yeah.
So since these are recorded, is it possible to find the constellation presentations you've done in the past on the website?
They aren't on the website, Richard. You can send an email to fundamentals at Tucson Astronomy, and I can share with you the links of the presentations that we do have archived.
Okay,
the email to contact is in the invite that I had the Zoom invite.
Yeah, I saw that in the notice that you sent for this meeting. So
Cool. Any other questions? If not, then
Yeah, I think the other problem Lynx has, it was almost in the zodiac, but didn't quite make it.
It doesn't have a, like I said, it's got no Greek background. It was just a bunch of leftover stars.
Doug?
Yeah.
Yeah, I I'm now in Arizona, but I'd like to mention that when we lived in Pima, which was very dark, I did the Constellation Observing Award for Astronomical League. And one of there you just observe the bright stars in that constellation. But like Lynx, one of the things that I really enjoyed doing after I did the drawing and sketching and so on, I observed that same constellation with binoculars. And
then
that
you can
was,
see the stars.
that was a lot of fun.
Yeah. Yeah, binoculars, and all of a sudden you can see most of the stars.
Yeah, because then you'd notice those 97 plus
Yeah,
stars you're talking
you see
about.
them. Yeah.
Hey, Doug, this is Gus.
Yeah.
Yeah, when I was doing the double star, I ran into that 12 Lynxes triplet.
Yeah.
On the list, it shows it's only 2 stars. And when I was looking at it, I noticed that the bright star was really weird. I even made a note of that it looks weird. And then I zoomed in, and it's actually two stars,
Yeah.
two really bright ones, and a smaller red
They're
one
very
on the
close
side.
together.
Yeah, really close. Yeah, because I was looking at it, why does that look so strange? So I had to zoom in and to resolve the two that are almost right next to each other. That's a pretty cool double star there.
Awesome. Thanks everyone for the discussion. Stephen, I think we're ready for you.
Okay. Whoops. Okay, we'll open this up. Should be there, and okay, can everybody hear me?
Yes.
Okay, so the main topic for tonight is Titan. And this is not going to be a really long presentation. It's just one moon, obviously. There you could teach whole classes on Titan and still not be able to cover everything that's known, but there's also a lot that is not known about it. But for this is just sort of a brief summary of sort of the broadest information of what Titan's all about. Titan is the largest moon of Saturn, and it's also a telescopic target if you have a small telescope. The problem with it as a telescopic target is it doesn't look like much. It's just a little orange, slightly orangish dot that you can see with the telescope pointed at Saturn. So I'm not going to include a observing it section in this. This is purely just talking about the moon and what is known from some of the space probes and observations that professional astronomers have done on Titan. So this is sort of a picture of what Titan looks like from space. It's not a very descriptive body because, as we'll be talking about, it is covered in a orangish haze that obscures the surface in visible light. So this is again from space for a human being, it would not appear to be very interesting, but as we found out by looking a little bit deeper, it is in fact an extremely interesting object. So some vital characteristics of Titan is about 1.2 million kilometers from Saturn, which places it quite a bit further out from Saturn than our moon is. Its orbital period is 15.9545 days, or essentially 16 days, which is actually something you can observe if you were to track it across going around Saturn. I've done that observation before just for fun, especially when the rings and the moons are roughly in line with our line of sight. It's easy to see it, watch it go back and forth. It's a little more complicated if you can see the other moons and if you see it when Saturn's rings are more opened up as they are right now. The orbital inclination is 0.348 degrees, which means it is very close to being in the equatorial plane of Saturn. And its mean radius is about 2,500 kilometers, which is about 40% of Earth's, or about 1.5 moons width of our moon. Its mass is about 0.0225 Earths, which is about 3 times the mass of our moon. Its density is 1.879 grams per centimeter cubed. Now that's significant for 2 reasons. First of all, it's obviously more dense than water, which would be 1.00 grams per cubic centimeter. So there has to be something in it that's made up of this more than just water ice. But at the same time, it's not all that dense compared to Earth or Mercury or a terrestrial planet. So a lot of it is made up of stuff that isn't terribly dense, but is denser than water ice. The surface gravity, interestingly, is about the same as you have on the moon, about 0.835 moons. The reason for that is it has to do with you'd be standing further from the center, and it's although it's more massive, it's not quite as dense as our moon is. So it comes out to be about an even wash with the gravity there. And the temperature, of course, is a very uncomfortable 93 kelvins, or minus 179 degrees Celsius. And that's critical to understanding a lot about the moon. This particular moon is that the temperatures there are extremely low. Not quite as low as you get it way out in the distant solar system, but temperatures do get extremely low, and that affects the chemistry of what's going on in the atmosphere and what's going on the surface. So keep in mind that when we talk about these kinds of things, some of these reactions would not happen the same way closer in, simply because the temperatures at which they happen would be much higher closer to the sun than they are at Titan's distance. I mean, chemistry is the same throughout the universe no matter what, but the rate at which reactions would happen would be a little bit different because of the low temperature. So here's just some size comparisons. Titan compared to our moon. As you can see now, these are rough. I didn't check to make sure they're exactly correct, but as you can see, Titan is a bit wider than our moon. And it's also quite a bit smaller than the Earth. So Earth's diameter is 12,756 kilometers, and Titan is about less than half of that. So is small compared to the Earth, but it is a very large moon. It's the second largest moon in the solar system, just barely smaller than Ganymede, which is a moon of Jupiter, and it is slightly larger than the planet Mercury, although it's not as massive or as dense as Mercury is. So this is a very large moon compared to some of the other objects in the solar system, which is one of its defining characteristics is its size. This is a rough image size comparison of the other objects in the in the Saturn system. Titan is clearly the largest moon within the Saturn system by quite a bit. It's not unusual, but it's different from the Jupiter system, where there are 4 large moons, the Galileans. In the Saturn system, there's only one really large planet-sized moon, and that is Titan. There are, of course, lots of other moons in the Saturn system, which are also very interesting objects, but we're not going to cover them here. And this gives a rough idea of what the size of the Titan would be compared to Saturn, which is the large curved object on the bottom. So the most significant thing about Titan, other than its size, is the fact that it's the only moon in the solar system with a dense, significant atmosphere. And I say dense and significant atmosphere because there are other moons that have very thin atmospheres, but this is the one that really has a really thick one that has a real impact on the surface. The surface pressure is 1.45 atmospheres, which means that it's actually higher surface pressure on Titan than it is on Earth. Not like Venus, which would crush a tin can and do all sorts of other things that aren't very pleasant. You could survive under these kinds of pressures without too much difficulty, but it would be more pressure than we have on the surface of the Earth. And the composition of the atmosphere is about 97% nitrogen, about 2.7% methane, which is variable slightly, somewhat like water is within Earth's atmosphere, and about 0.2% hydrogen. So it's not unlike Earth's atmosphere in that it's made of mostly nitrogen, but you'll notice that Earth's atmosphere actually is made of about 80% nitrogen, 75% nitrogen by comparison, whereas most of Titan's atmosphere is nitrogen. And Titan's atmosphere also lacks the oxygen, and with some exceptions, just the faint traces of carbon dioxide. So it is somewhat Earth-like, but not exactly. Also, Titan has much more methane in the atmosphere than Earth does. On Earth, the methane is a trace gas, whereas in Titan it is a substantial part, and it does play a large part in the weather of Titan, as we'll see. So a few things about the discovery. It was discovered by Kristen Huygens, and I hope I'm saying that correctly. Date was March 25th, 1665, and there's a picture of Christian Huygens. He was a very prominent astronomer at the time. He, of course, had other discoveries that go to his name, of which I'm not as familiar, but he is probably best known for this particular discovery. Originally, he called it Luna Saturni because at the time it was being that it was the only large moon of Saturn. It was the only one that they could see. Notice that the date is 1665, which is not that much later after the moons of Jupiter were discovered, which I believe was 1609. So we're talking about within 50 years or so, they had discovered the first moon of Saturn. And the way he did this was rather interesting. I don't know if this particular discovery was made with one of these, but he built these telescopes that were refractors. Now, these are refractors that were only 2 or 3 inches in aperture, but they were so long that they were like the mass of a ship or the spars on a ship, and they would actually bring in sailors to hoist these things on a mast so that he could stand down at the bottom and look through the telescope. The reason for this is because the system for working out aberrations within a refractor had not really been improved much since Galileo, and as a result, there were no second elements, and there were none of the third elements like we have today in apochromatic and achromatic refractors, and there were a lot of other aberrations that were in these telescopes as well. So it's kind of a wonder that he was able to see anything at all, given the fact that the state of the telescopes at the time looked something like this. And of course, this explains why the Newtonian reflector was such a big deal, because you didn't need a whole naval crew to be able to hoist one of those things for just a few inches of aperture. And Huygens did, in fact, use these. I don't know if he designed them, but they are contemporary with him and things that he used for some of his observations. Later designations of the moon were Saturn IV, starting in 1686. That was after some of the other moons had been discovered. And it was named that because at the time it was believed to be the fourth satellite from Saturn out of, I believe, 5 or 6. It was also sometimes called Saturn's ordinary satellite. And also the IAU still maintains the designation of Saturn VI. We now know that there are, in fact, many more moons further in than just this 6 or the 5 that were listed in that designation, but those were discovered primarily through later probes that came through the system. Of the bright satellites that are obvious from Earth, it is the 6th out. Titan was proposed by John Herschel, who was the son of William Herschel. And the Titans were a race of immortals who preceded the gods of Olympus in Greek mythology. And they, I have heard, I don't know if it's apocryphal or not, but one of the reasons why Titan was proposed for this particular moon is because at the time it was thought that it was either the largest or one of the largest in the solar system. They did not know about a very important fact yet, which was that Titan has an atmosphere, which of course distorts our estimation of how big it is when it's looked through a telescope. So that was one of the reasons for it. And when we talk about the nomenclature on Titan, most of the names are much more recent that occur, have been created since the both the Hubble Space Telescope and then the Cassini mission went by and was able to map out some of a lot of the features on the surface. Today, some of the surface features, especially the regions, are named after sort of fantastic paradises, and then most of them are named after huge mythological beasts. And we'll look at a few of those in just a few minutes. So early discoveries, 1944, Gerard Kuiper identified that Titan has an atmosphere, and he took spectrographic measurements to reveal the presence of gaseous methane. And of course, later it was determined there was also a fair amount of nitrogen in there. He also determined, based on the characteristics of the gas, that the atmosphere is probably hazy. Although if you look at some of the early depictions of paintings of what they thought Titan looked like, they often do it under blue sky. But in fact, they had a good idea that the atmosphere was hazy from fairly early on. Early exploration, Pioneer 11 traveled by Saturn. I forgot to note the year. I think it was 1977. But it confirmed the temperature and mass of Titan, and it saw hints of a bluish haze. The camera on Pioneer 11 was not even up to the standards of what went on Voyager, which actually passed through the system just a couple years later. And it was a case where what they got was sort of a grainy image that wasn't know, it's not a bad image, but it certainly is not what we were able to get later. But they were able to detect some of these hazes high in the atmosphere. And there's some interesting chemistry that goes in them that we'll talk about in a bit. So the real exciting probe that revealed a lot about the moon eventually was Voyager, the Voyager 1 in particular. Now Voyager 2 went by Saturn as well, but there's an interesting story with that. And again, I don't know if it's apocryphal or not, but the story I've read was that a primary mission objective from the beginning was to get a good look at Titan. But it was also considered sending both probes onto Uranus and hopefully onto Neptune, or possibly, if they got really lucky, sending Voyager 1 onto Pluto. The mission that Pluto was always a stretch. It wasn't really in a good position for it, and that was kind of an idea that was just thrown around. But the idea of sending Voyager onto the other gas giants was very much something that was designed from the mission as part of the grand tour from the beginning. But the mission planners decided to use the Saturn flyby to shift Voyager 1's trajectory to get a close pass by Titan. So they didn't exactly sacrifice the probe. The primary mission was always to see the Jupiter system and the Saturn system, and then maybe get onto the outer gas giants. But they did decide to kind of send it in a different direction just so they could get an idea of what Titan looked like. And this is what they saw. So that's the Voyager 1 image, I think, with some enhancements. So if you had just launched the probe at that thing and basically ruined any chance of getting onto Uranus and Neptune to have a good look at Titan, this might have been slightly disappointing as a image to get back. What you're looking at, of course, is the haze layers that exist within Titan's atmosphere. Well, Gerard Kuiper had already proposed that there was haze in Titan's atmosphere, but they didn't know how much, and so they were naturally slightly disappointed with just how hazy the atmosphere really was. They were hoping to get a look at least some of the features on the surface, and as it turns out, the cameras that Voyager carried were primarily in the visible wavelengths and therefore didn't penetrate the hazes very well. And so as a result, this is the image that they were able to get. They also were able to get a better look at some of those high altitude hazes that glowed in sort of a bluish light that Pioneer had picked up on. So they were able to confirm that. But in terms of getting a good look at the surface, that would have to wait. So the next major mission to Saturn was the big one, the Cassini-Huygens to Saturn. That was a much larger probe that carried a lot of really, what were at the time very sophisticated instruments, and more importantly, it was going to go into orbit around Saturn and therefore be able to make multiple passes around the moons and the planet itself. The launch date was October 15th, 1997. It launched, ironically, on a Titan IV rocket. That was not, the Titan was a name used by for missiles for years, were converted into launchers. I think you guys know that story better than I do. But that was the Titan IV rocket. The time in transit was about 6.5, 2/3 of a year. It made several flybys of inner solar system objects and then used Jupiter for the final kick out to Saturn. And Saturn arrival was on July 1st, 2004. And I'll note what Huygens is in just a minute, but its landing was January 14th, 2005, which is about a year later. So this was the Cassini spacecraft, and it obviously contains a bunch of different instruments which were meant for different purposes. Some of them were meant more for Saturn than for the moons, but definitely had roles to play within the moons. Others were meant for the entire system. The remote sensing palette contains the main cameras, and unlike Voyager, which came primarily with a camera that was focused on visible and near-infrared and UV image wavelengths, Cassini came equipped with cameras that could see fairly far into the infrared. And they had done this on purpose, thinking of Titan, because they figured that with the hazes, if they could go somewhat further into the infrared than Voyager had been, they'd be able to penetrate them much better than they had with Voyager. And so the cameras were purposely designed for Titan as much as they were for Saturn. Also, you'll notice that very large antenna on the top. This was a modified version of one that had come from Voyager, and I think it was even one considered used as one that was, I don't know if it was a spare, but it looks an awful like the Voyager antenna. But it also had an extra feature, which was that it could be used as an active radar scanner, much like the scanner on the Magellan probe that is surrounded or that orbited Venus a few years earlier. And the intention with that was to create radar scans of the surface. So between these infrared images, which could get a broad look at sort of the features on Titan at low resolution, and these radar scans, which could get much narrower fields, but could get a much higher resolution, they were good. The Cassini probe was built as much for Titan as it was for Saturn itself. So the Huygens probe is the thing that in every picture I tried to find had the Huygens probe pointed away from the viewer, but it actually is a critical thing. And the Huygens probe was attached to the side of Cassini. It was built by the Europeans. So Cassini itself was a product of the Jet Propulsion Laboratory in Pasadena. I think it was Lockheed was the main contractor. But the Huygens probe was built by, I think, Thales Alenia, and it was a ESA mission that it basically hitched a ride on the side of Cassini and then used it as a relay for the actual landing. And at a certain point, it was designed to pop off the side and interface with Titan's atmosphere and land on the surface. Of course, it can't carry. It didn't carry a nuclear battery like a lot of the probes, the Cassini probe itself. So the batteries would only last for a few hours for the descent and maybe an hour or so on the surface. And then at the same time, it couldn't carry solar receptors or collectors because there's so little sunlight on the surface that it wouldn't be able to power the probe. So it was meant for just a few hours of a mission, but it was ended up being very successful. There is another story, this one not apocryphal, that midway through the transfer part of the mission, they discovered that if they took into account the Doppler shift of this little Huygens probe heading towards Titan away from Cassini, the radios that were meant to receive Huygens transmission on Cassini, and then so the Cassini could beam it back to Earth, were actually, if they encountered for the Doppler shift, were not tuned to the proper signal. And so they had to change the mission profile in order to accommodate the Doppler shift problem, which is one of the reasons why the probe was, the Huygens was launched at a different time than they had originally planned. And there's a whole story behind that one as well. But Huygens did get off, and it was a very successful part of the mission. The basic idea is it comes through the atmosphere, and much like a Mars probe, it has the heat shield. It was traveling at some speed. Cassini was already in orbit around Saturn when it released Huygens, so it wasn't going as fast as it could have been, but it needed the heat shield, and because it has a thick atmosphere, it could use a parachute. It then would float through the atmosphere, slowly coming down to the surface, and take measurements of the atmosphere itself, plus take pictures of the surface as it was landing, and then hopefully, if everything went right, it would be able to transmit from the surface for a few minutes. And that was the basic mission outline. Again, there was the batteries are only meant to last for a few hours at most. And so once the batteries died, that was the end of the mission. But it would give us our first glimpse of the surface from the surface. It was also, interestingly, the first time that a human-made object had landed on a moon other than our own. That's interesting considering the fact that other attempts have been made to land on the moons of Mars earlier than that by the Russians, and they, of course, it failed miserably. We got to have that particular distinction in terms of the landing. This is a very complicated diagram that shows what the Cassini mission looked like once it had entered orbit around Saturn and the path that it had taken. The point that I'm trying to make with this is you'll notice that early in the mission, First of all, Cassini is relatively close to the plane of Saturn's moons because the primary mission was to look at the moons and the planet itself and get high resolution images of as many of the moons as it possibly can. It was also on a really quirky orbit in that it was designed, at least early on in the mission and for most of the mission, to pass by Titan for every orbit that it made of Saturn. That later changed during the last part of the mission. They actually kicked it so far in such a high inclination orbit it could no longer return to Titan. But what that meant was that for every orbit of Saturn, you also got a pass of Titan. They gave it another look at Titan. So they could either use the photographic instruments, they could use the scanners for to look at the different materials that the atmosphere was made up, or they could use the radar, not necessarily all at the same time. So as I said before, the mission of Cassini itself was as much to see, to explore Titan as it was to explore Saturn itself. And a part of the way it did this was by making these scans as it passed over past the moon. And it would basically bounce radar off the surface on these strips that would then bounce back to the satellite. And by measuring the time differences between when the signal was sent out and when it came back, they could then create a surface map or a topographic map of those swaths of the surface that it passed over. This is an idea of what Titan's surface looks like in infrared. So these are patchworks of images and mosaics of images that were put together by the infrared cameras. And as you can see, it's not very high resolution. You can make out some dark patches and some light patches. These have been enhanced somewhat compared to the original images, but it does give a general sense of the global picture of what Titan looks like, because all of the radar gave us very high definition images in terms of the topography. They only covered about half the surface in the whole time that the mission was there because they covered such narrow strips. And so getting a picture of what the whole moon looked like was really something that they wanted to do with the infrared. And again, these are somewhat false color because you're using an infrared camera. This is what those strips look like if you saw them basically placed across the moon, which would be these strips that the radar was taking. And the light areas are areas which are relatively have the difference in the colors is basically the amount of reflectivity of the surface, and that generally depends on both a little bit of altitude, but also the whether the surface is nice and smooth or relatively good at scattering radar signals. This is a geologic map that has been created subsequent to the mission based on both the radar scans and the infrared images. They capture what the different terrain types are on Titan. Most of Titan is just plains, and there's especially away from the equator, there's not a lot of topography. But when you get close to the equator, you notice that there's a lot of dune fields. So Saturn or Titan, ironically, is a bit of a desert, and the reason is that the temperatures at which the gases that liquefy are actually fairly high for those gases, mainly methane and ethane, and so you only get a lot of rainfall, so to speak, away from the equator. So because of that, you get sort of deserts around the equator, even though by deserts we're talking about 97 degrees Kelvin. So we're talking about incredibly cold deserts, but there is some moisture that comes in, but that's not where the main storms come from. You'll also notice up towards the North Pole, there are these blue spots, and those are the lakes of Titan, which received a lot of attention during the mission, and which we'll cover in just a minute. Those are lakes that are made up of liquid methane and ethane, and they are the only other surface bodies of liquid in the solar system that we've been able to identify so far, other than the oceans and seas of Earth. They are made of a completely different material and have a very different chemistry than Earth's oceans and seas do, but they are in fact liquid. And then there are just a handful of craters that have been visibly recognized, which shows that the surface is not young, but fairly young, largely because of wind and weather erosion. And that's and then the brownish areas are areas of highlands that are sort of hummocky and have a lot of texture to them rather than smooth surfaces. This is a topographic map of what Titan looks like. So most of the highlands are towards the equator, and we're not talking about huge mountain ranges in terms of height. We're talking 2,000 or 3,000 feet or so in altitude. But it wouldn't, the topography on Titan probably wouldn't be any greater than here in Tucson, if less than that. But you'll notice that the areas near the poles tend to be flatter and lower in elevation. Again, these were made with the radar maps of the moon and kind of pieced together from that. Titan does have craters, but as you can see, they're fairly well eroded. And that tends to be a pattern that we see across the surface of it. There's a fair amount of erosion. That's to be expected given the fact that it has both a thick atmosphere and precipitation. So anything that happened there is going to wear down over time, much as it does on Earth. Interestingly, Huygens did not pick up strong winds at the surface, maybe just a couple miles an hour. The difference there is because of the greater pressure, there's more carrying power to the wind, but at the same time, there was not noted there were really strong winds at that time on that particular part of Titan. And of course, it landed near the equator, so it didn't get a good look at what goes on closer to the poles, but it didn't detect really strong winds. And there's some more craters, as you can see, sort of worn down. They are there. So the surface is probably a little bit older than Earth's, but a lot of weathering and erosion has happened. There's also these highlands, which are sort of rough areas and mountainous. This again shows that our radar images are not seeing snow. You're just seeing areas which are of higher and lesser reflectivity on the surface. And there are some mountain ranges and the like. Again, these are close to the equator. And this shows sort of where those areas are. Again, the altitude on these things is not very great, about 3,000 or 2,000 meters, about 9 to 10,000 feet. So about what you have here in the Tucson Basin with those mountains. Certainly nothing as big as Mount Everest or even Mauna Loa or anything like that, or the mountains of Jupiter, or not Jupiter, of Mars. Nothing like that on Titan. A lot of dunes near the equator, and these are the radar images of the dunes. This faint streaks that you see are the different kinds of dunes, which suggests that there has to be some kind of a wind on the surface. Now, the dunes are made of something slightly different than sand. It's thought that there's some kind of organic material that is probably precipitated out of the atmosphere. They would have roughly the consistency of coffee grinds. But they are, in fact, dunes just like you'd have on Earth, and you can, they would look much like that. I don't know much about what the altitudes are, if that was particularly determined, but they're not very high. Again, more dunes, and you can see where the wind was coming from, and also the fact that the dunes exist suggests that there's winds, and again, this is primarily around the equator. More dunes and some obstacles to the dunes, and the winds kind of shape the dunes around the obstacles. Lakes are a key feature of Titan because, as I said, they are the only surface liquid that we've discovered so far in the solar system, and there's not a lot of other targets to look for that we haven't seen yet. But they do exist. They have been a major source of study. These, again, are radar images that show sort of the broad picture of what the lakes look like. The lakes, and we'll go into the composition of the lakes in a minute, but they are liquid. They are extremely cold, and they're made of a completely different material than any of the lakes on Earth. So this is one of the larger lakes. As you can see, there are edges. The edges are fairly defined. Again, more look at those large lakes. As you can see, there were different passes, and they were getting different resolutions depending on the pass. It's also possible that the surface conditions may have been slightly different. Again, they didn't detect large waves on the lakes, but they may have detected ripples, which suggests that there were at least a little bit of wind, but not a lot on the lake surfaces. So this is unfortunately, the image didn't come out very well, but it shows the names of some of the different lakes: Kraken Mare, Legia Mare, Purgus Mare. Again, Mare means sea in Latin, and I'm probably completely butchering the names as well, but they are named after huge mythical beasts. There are rivers on Titan, and several of them. Those lakes are fed by rivers. And this is a picture of one that's been compared to the Nile. So on the left is Earth's Nile, and on the right is Titan's version of that. Of course, so the material that's in the river is very different than the material that's in the Nile. And possibly a volcano. So this is I put a big question mark on this because this is hotly debated by the planetary scientists. Is this or is this not a volcano? Well, it's a crater. It's obviously not an impact crater, but it is, first of all, the only one that they clearly identified. And also, they don't know if anything is coming out of it. There could be other geological explanations for what that is, causes that particular feature, but it could be a volcano. If we're looking at volcanism on Titan, we're really talking about cryovolcanism. So it would be water and other materials that come out on Earth as a liquid that would come out as liquids from this and then form icy mountains around it. It would not be liquid rock in the sense that Earth has liquid rock. It would be liquid rock on Titan standard because Titan, the upper layer is mostly ice anyway, but it would not be hot, glowing lava like Earth has with liquid rock. It would be mostly ice and other materials, or mostly water and other materials that are coming out of it. And this is a comparison between the supposed Titan volcano and some of the volcanoes on Earth, again, giving some idea that there might be a comparison. Again, this is hotly debated. Some scientists definitely think it's an ice volcano. Other people say, no, not so fast. So the question of cryovolcanism on Titan is very much an open question. So Huygens also made images as it approached and landed. This is one of the images that was made of the surface as Huygens came in for a land. I've never been able to make much sense out of the Huygens images and the fact that you can see some features which look like hills and rolling hummocks, and then a few things that look like not water channels, but they look like water channels, but they're not water channels. They are channels of a kind. And then just this open surface of flat open plains. It did land near the equator, which is where most of the topography is. So it shows that part of the moon, and that's what the surface looked like as the probe was coming through the atmosphere. And these are other images showing at different altitudes. So at the top is while it was still coming through the haze, and then showing lower and lower altitudes as the probe got closer and closer to the surface. And the probe did manage to make it to the surface itself and report back. This is a picture that was taken out of a side camera showing what the surface looks like. Those are not boulders. Those are small little rocks. So this is so close to the surface that we're seeing not exactly pebbles, but they wouldn't be very large either. We're not talking about a foot across. We're talking about a few inches at most. Which is interesting. There were gases that were detected sort of outgassing as the warmth of the probe warmed them up, and there's some suggestion that there was maybe some kind of somewhat liquid material that was been solid when the probe landed and then vaporized. I'm botching my chemistry terms up here, but the point being that there is interesting chemistry on the surface, but what you see is mostly look fairly dry. I've heard it described as being like the consistency of creme brulee once they landed on the surface. The thing here is what we're looking at are rocks in the sense of the physical sense, but they are made mostly of ices. So it'd be water, ice, and other materials that are normally liquid or gas on Earth's surface that are so hard that they basically have the consistency of rock on Titan. This is an atmospheric profile of what they found going through. So there's a Tholen huge precursor to organic or biological I'm gonna say this, they're precursors to the kinds of stuff that make up you and me, but they're a lot smaller than that. But they're also bigger than just methane and carbon dioxide. So there's then found layers of condensate, and then closer to the surface, they found methane clouds that rain methane down onto the surface. Again, there's some question about whether there's water and ammonia volcanism, and we saw some of the features that are on the surface in terms of liquids. So it's a very complicated atmosphere with a lot of different parts. This is showing some of the chemistry that's going on. The thing to focus on, and I'm not an expert in what this chemistry looks like, other than to say that there's a lot of particles coming in from Saturn and from the sun, and they interact with the carbon molecules and the nitrogen in the upper atmosphere and form larger molecules. And those molecules fall down onto the surface gradually. They also make up some of the hazes that are seen in the pictures of Titan. So this is an example of some of the chemistry. Again, we're not talking about DNA here. We're talking about stuff that's bigger than methane and ethane, but not super long chain molecules. But it is a fairly complicated chemistry. And again, that stuff is up in the higher atmosphere. You have some of these tholins, which are a little bit bigger than that. And gradually some of the stuff will just settle down into the lower atmosphere where it sort of gradually falls down onto the surface. But until then, it's blocking our normal images of our visible images of the surface, and is producing some really interesting chemistry that may be precursors of what the kinds of chemistry was that was going on Earth billions of years ago, which is one of the reasons why it's of interest. It wouldn't be exactly the same, but there might be parallels. The interesting thing here is way up in the stratosphere and the mesosphere. So we're talking up to between 100 and 450 miles, which is very high up. Titan has a big, thick atmosphere in part because it doesn't have a lot of gravity to squeeze it down. But that's where you have these tholin layers where the ultraviolet light and particle radiation coming from Saturn or from the sun and Saturn is basically causing these long chain molecules to build up. And that's one of the things that we see, I believe, with the detached haze layers, that bluish thing that we saw some of the images from Voyager. But that's what's coming up with that. And again, a lot of cool chemistry going on the surface. You have the methane and the nitrogen being bombarded by ultraviolet light, and you have these particles coming in from Saturn, and so the simple molecules are being converted into larger and larger molecules in the atmosphere. Again, not DNA, but stuff that's bigger than methane and ethane, including these tholins. So what exactly is a tholin? Well, tholin was a term that was created by people like Carl Sagan when they did these middle Urey experiments to basically try and produce living things out of the primordial atmosphere of the Earth. And what they got was this sort of brownish reddish goo was made out of those processes. And it's thought this stuff is fairly rare on Earth today because it breaks down in our atmosphere, and there's a whole bunch of chemistry that would wipe these things out. But in early Earth's atmosphere, these might have been the precursors of the molecules that eventually made living things. And so these things being in the atmosphere is pretty exciting because it shows some of that chemistry was going on there. But this is what a tholin looks like. They're usually typically a reddish brown thing. And beyond that are there large chain molecules. There's again a major area of debate. These are all amino acids. Now, no amino acid has ever been detected on Titan, but just to give you an idea, these larger chains, what that would look like, who knows? The Huygens was not able to determine one way or another, and neither was Cassini. Titan, having an atmosphere, has weather. These are some clouds that cropped up towards the polar regions. Titan also has seasons because it's in the same plane as Saturn, and because it has very little orbital inclination to Saturn, it has the same seasons as Saturn does. So every time Saturn goes around once and has its own series of seasons, then Titan does as well. This is the northern polar region, I believe, coming into sunlight as spring begins, as northern spring begins. And as you can see, there's cloud layers there, and the weather changes depending on the season. A lot of the weather is towards the polar areas. And again, this is just some of the clouds that showed up. It wasn't certain at first if there would be clouds on Titan because the hazes block the view from Voyager, but there are in fact some clouds that form on Titan. This is a methane ice cloud that cropped up as a storm on Titan while Cassini was there to observe it. And as you can see, again, a determinator, and it would have been capable of producing, some methane rain and the like. So big question with Titan, is there life there? Well, at first, very broad glance, it'd be really exciting to think that this is a place where life could exist. There's the liquids on the surface. There's some other features, which we'll talk about in a second, that could really apply to that. But when you look at the details, it's much harder for it to occur than one might first think just looking at the broad dynamics of the moon. We've already identified that there's some very complicated chemistry going on in the atmosphere thanks to these interactions between UV light and methane and nitrogen and everything else. But does that mean life? It's a big leap between these large molecules and living things. And there are certain things which just are missing that make it really difficult to see life, especially on the surface. So one thing is the composition of the lakes. So the lakes are made up primarily of methane, which is this molecule that's on the left, and ethane, which is the molecule on the right. It's actually much more methane than they originally thought. They thought it would be more of an ethane thing, and it's actually more methane than they expected. But the point being is that these are the primary things that make up the molecules that make up the lakes. Is important because neither of these molecules are polar, which is a characteristic that certain molecules have where they have a slight charge on one end and the opposite slight charge on the other. Methane and ethane are nonpolar. And the reason that's important is because most of the molecules that make up living things are polar and have to be in a polar solvent in order to form the kind of liquid forms that we're all made of. So that's really critical in terms of the chemistry that goes on the lakes. Is very, very different from the chemistry that goes on in our oceans, because the basic material that you're made of has a whole different set of properties than liquid water does. What about life on the interior? And then, of course, there's the fact that it's incredibly cold. And so there isn't much of an energy source other than maybe the stuff raining down onto the surface that would make it possible for life to happen. So the lakes are not considered a great place to look for life as we understand it. Now, could there be a whole different chemistry of life out there? Who knows? But based on what we understand about life on Earth, it'd be very difficult for living things as we understand them to live on the surface for all those reasons. Now, what about life in the interior? It was identified by Cassini that Titan does have liquid water ocean deep within the interior, hundreds of miles down. This was done by looking, I believe, at the way that Saturn's magnetic field flows through the moon. And it was identified as probably having a liquid water ocean deep within the interior. That said, the interior, this water ocean is incredibly deep. It'd be very, very difficult for us to ever access it. So there's a lot of speculation about what would go on there, and we may never have an answer because it's simply too far down to ever access it. But one of the things I want you to think about with this ocean is the first thought was, oh, it's like a Europa. It's a great place to look for life. And there's a big problem, which is that if you'll notice towards the bottom of the picture, there's a second layer of ice that surrounds the inner layer, which is mostly rocky stuff. In order to form a Europa-like situation, you need to have rock in contact with the ocean itself. And they think because the reason there's that second layer of ice is because the pressure is so great at that depth that the water reforms into ice and resolidifies. And because of that, it's thought that there's not a lot of material reaching from the moon's interior up into the ocean. It's pretty much sealed off. And so stuff coming down or coming up from the interior interior like you have on the bottom of Earth's oceans, where you have the super thermal vents and things like that, would be very difficult on Titan if they're right about the second layer of ice. Now, what about stuff coming from above? That's a much bigger question, because we don't really know the dynamics of this ice crust. We know that it's very thick, that it's at least 100 miles thick and probably thicker than that. But does it have tectonics? Is there stuff making it from the surface down into the ocean and vice versa? Just no way to know at this point. And it is conceivable that some of that stuff coming down from the surface could form as a kind of a fuel for life, but that is a very, very big if at this point. They simply don't know if that's possible. So we see this image of lakes and things and volcanoes and the like, and there's a lot of questions about whether that's actually the case. And even if there's stuff coming up, even if there are volcanoes, they probably are fed from much closer to the surface than this ocean. And so even then it's hard to determine if there's any connection between the surface and this deep interior. So again, it's not impossible, but it's a really big question at this point. It doesn't look terribly promising. Now, that said, this is all based on our assumptions of how life works on Earth. Is there some kind of completely different life system out there? Who knows? Probably not, but since we only have one sample to work with, it's really hard to rule it out completely. But Titan would be chemically an interesting place to look at, simply because there's a lot there that happened, billions of years ago on Earth that no longer happens because our atmosphere has a different chemistry that would be really fun to get a look at. There's also this methane mystery, which is really interesting, which is that Titan's atmosphere has a lot of methane in it. And it shouldn't, because over time, all that UV light and all that particle radiation from Saturn should convert most of the methane into larger molecules that then rain down on the surface. And yet something seems to be replenishing the methane pretty consistently. What that is, probably something geologic, but as some writers point out, whenever you have one of these imbalances where there's something there that it shouldn't be, it's always an indicator that there's some interesting chemistry going on. And whether that's life or not, who knows? We need obviously a lot more research, but it is at least interesting. I'll leave it at that. Future exploration, this is Dragonfly. It is a mission which has been approved and which is being in its design phases and is going to be launched. It'll be launched at the end of this decade or the beginning of the next. And of course, there's a lot of, whenever we talk about a NASA mission, you never know when it's actually going to get off the ground. But it is a quadricopter that is going to go to the surface of Titan near the equator. It won't get near the lakes. It's going to be an equatorial mission, but it'll land there, and because Titan has such a thick atmosphere, we know that that we can run a helicopter in there and it'll work. It's not like Mars, where there's a big question because about that helicopter that's on the Perseverance lander, because on Mars the atmosphere is really thin. On Titan the atmosphere is really thick, so we have a really good idea this is going to work. It is, I think, one of these ones that's going to have obviously not. It'll have a nuclear battery on it, which will make it pretty heavy. I don't know how they're working the dynamics of the engineering, but it'll be able to land, fly to a different spot, land again, take some measurements, fly to a different spot, and then take some measurements and take pictures at the same time that it'll send back to Earth. So this is a really complicated mission, but one that's really exciting because it'll get a look at multiple spots on the surface as it sort of flies around on in the side of the atmosphere. And this is how it plans to land. It'll come through on a parachute, drop off its heat shell, and then it will the little rotors will turn on and it'll land that way, and then it'll take the first measurements and then fly off to the next spot. And there'll be some chemistry experiments and things on it to get a sense of what the dunes are made out of and what the surface is made out of. And in the very far, far, far future, this is science fiction at this point, there's talk about probes that would go into the lakes of Titan and photograph the bottom, if they can get that far down, or at least get a sense of what exactly the lakes are made of. They'd be using submarines at that point. Again, this is decades in the future, something that was kind of a pipe dream for NASA, to be able to get something in those lakes and be able to determine if there's anything interesting in there. Chances chances are this is not, they won't find anything other than just icy rock at the bottom, but who knows? And that is it. I just dumped a lot of information on anybody. Any questions about any of that?
Well done, Stephen.
Okay. Thank you very much.
That was fantastic. I love the idea of the mission of the helicopter. When are they planning to do that? Is that just in the beginning stage?
Well, it's been approved, which means that the mission plan is going ahead. They're in the design stages now. Most of the designing, I'd assume, is already done, but they're not quite at the point where they're going to start assembling it yet. But they will have it up, I think, they're talking the early 2030s, it'll be on its way. It'll take, the better part of a decade to get out that far. Again, it's got to whip around the inner solar system and out towards Jupiter and all the rest of it in order to pick up the speed to be able to get out to Saturn. So once it's in space, it'll be a fairly long ride out to Saturn, but it will happen hopefully within our lifetimes, meaning probably the 2030s or 40s. Would be the primary time for the mission. Again, at this point, as I said, the mission has been approved, so it's no longer in the proposal phase, but they're not, as far as I know, building hardware yet.
Whose lifetimes?
I won't comment on that.
Thank you for compiling all of that. I'm sure it took quite a while to put all of that together.
Thank you.
Bernie, with all this new technology, you're going to live at least till 120, so don't worry.
Yeah, I'll be the $1 trillion man if that's the case.
Okay, so I'm going to end the recording